Everyone, today we are going to talk about American Sign Language recognition using multimodal transfer learning. So hearing loss occurs due to the damage in the auditory nerve in the inner ear. So there are various medical means which will help cure this loss. However, these are not very reliable and the succession rate is very low. American Sign Language is useful where there are finger spellings for all the alphabets, which forms effective means of communication. And the deep learning convolutional neural network models can be used to solve this problem of recognizing the sign language. This is a basic block diagram of our model. On the left-hand side, as you can see, whatever be the hand gesture, like alphabets between A to Z or digits between 0 to 9, or any kind of hand gesture, when these are provided as inputs to the model, the deep learning algorithm detects the gestures and converts it into the word or a single character. Talking about the existing solutions, the first solution talks about multiple convolutional networks connected in parallel, wherein the features are extracted from the last few layers of CNN. And for the dimensionality reduction purpose, PCA technique is used. PCA is, however, computationally time consuming. So this is one of the drawbacks. In the second approach, machine learning and deep learning algorithms are used for feature extraction. And as we all know, machine learning requires that we need to provide handcrafted features, which is time consuming and can cause errors. And most of the solutions available today make use of the alphabet data set for training and evaluation purpose. So this is a drawback because generalization to other kind of data sets like digits and gesture will not lead good results. The first technique used in our key design approach is two pre-trained models are used in series, and then the weights are transferred between each layer of pre-trained models from the first model in the cascade to the second model in the cascade. So this makes a weak learner a strong learner, which we generally call it as ensemble technique, and this is also consuming less time. Towards the end of the architecture, the softmax probabilities from each cascade is concatenated, which reduces the bias, if in case there is any, from a single model or multiple models. And our model has been generalized not just for alphabet data set, but also for 10 digits and 16 hand gestures. This is the block diagram and the architecture of our model. So the data set is provided to every model in the cascade. So the first cascade consists of VGG16 in series, and the second cascade consists of MobileNet connected in series. So the weights are fused between each layer of the pre-trained models from the first to the second model. And the probabilities are concatenated to predict the alphabets, which can then be generalized to digits and gestures. Some of the hyperparameters used in this technique are learning rate of 0.0001, optimizer being Adam, batch size of 60, epochs of 10, and activation function being ReLU. Some more details regarding the approach is the dataset is from Kaggle, consisting of A to Z alphabets, each of 100 samples, and test samples of 260, consisting of 0 to 9 digits and 16 gestures. So when we look at the results, we can see that MobileNet performs better than VGG, wherein the validation accuracy in red is about 90% in comparison with the VGG, which is around 60%. And as you can see, the curves are not overfitting. So looking at the other details of the results, the evaluation has been generalized to digits and gesture data set. So the second model in the cascade performs much better than the first model. And overall, MobileNet performs better than VGG16. So with such architecture, we can have convenient way to recognize the alphabets, digits, and gestures, which will be useful for the hearing impaired community. Thank you.